employees leaving. So moving on to the shark attacks. So the point of the poisson is that you're counting the number of occurrences, and you have to have that the probability of an occurrence has to be the same in every interval of equal length. And provided the intervals are non-overlapping, if they're of equal length, or even not, they are independent. So you can't have it such that the sharks all attack and eat well, and then they don't attack for a while. It's the same probability of this, a certain number of attacks in every interval that's non-overlapping. These are independent. You'll notice it doesn't really take much to define such an experiment. And I think the article actually mentions this. There's another way of getting the exact same information. On the one hand, you have the number of attacks in a given time interval. On the other, you could measure what? To tell you the same information.
No attacks.
What's that?
No attacks.
How are you measuring no attacks? I don't think you can do that.
Period between attacks?
Exactly. You can measure the time between attacks, right? If you had written down all the times between attacks, and you'd written down the number of attacks in every, say, minute, you would have the exact same information, right? Now, of course, with the poisson, you really have to have the exact same, number of attacks in every hour, the number of attacks every day, and so on. Anyway, the nice thing about that is you therefore have two very different approaches to the same thing. Depending on what you're doing, you choose whatever's easiest. The poisson is easier in the sense that it's discrete. So to some extent it's more intuitive, but the exponential, which measures then, which is the distribution then of the time between occurrences, is while continuous, it's easier to work with. Mathematically, it's very straightforward to work with. This is the probability distribution for the poisson. Do not expect that to be intuitive, but it is. It actually just comes from an expansion of the exponential. The exponential e is just a universal constant. It's the number 2.7828 and so on. It never ends. And by plugging in values for x, you get a probability for x. Is there an x so large that it is impossible that it'll happen? In other words, that it has a zero probability of happening. No, because the numerator never goes to zero. But the factorial grows faster than any polynomial, so it will go to zero quite quickly, or go towards zero quite quickly, and in fact quickly enough that when you add them all up, you will in fact get 1 to be the final sum. Well, as an example, we can count the number of people that show up at an emergency room, and if you do this long enough, you can just calculate that you figure the average rate of arrivals is 6 per hour. Now look at a half hour. If you have a Poisson situation, you then have, on average, 3 per half hour, which is now your parameter mu. You're interested in calculating the probability of seeing exactly 4 arrivals in the next half hour. So you plug in mu to the power of x, e to the power of minus mu, divided by x factorial. Gives you a probability of 16.8%. So notice that all you've done is calculate the average rate of arrivals, and based on that, you can come up with a fairly precise estimate for having 4 arrivals in the next 30 minutes. Oddly enough, at least I think it's sort of strange, this is a remarkably accurate distribution. Even when you get violations, the violations aren't that large. So, I mean, sure, there's sometimes you do, but most of the time, the Poisson is really good for things like the number of arrivals at the store, the number of, apparently shark attacks, when you're looking at the rate at which the Earth is hit by meteorites, all sorts of things. The Poisson is truly remarkably useful. and you can come up with fairly accurate numbers. So if I ask you to come up with a probability that you had 4 or fewer arrivals, how would you calculate that?
Same thing?
Probability of 4 plus 3 plus 2 plus 1.
Yeah, I think Dave's solution is a little easier in this case, a little louder.
Probability of 4 plus probability of 3 down to 1.
1?
Yeah.
0.
Very good. You could in fact have no arrivals, right? Certainly possible. Okay.
What happens if somebody leaves?
What's that?
Somebody leaves, it's like a -1.
That is an excellent point that would violate the spirit of the experiment, so that can't happen. It's like the Hotel California. That too. Okay, no, this isn't working. Usually what happens when you have people leaving is you set it up so that you're counting arrivals, then you use an exponential distribution to calculate the amount of time you're at different stations, then you count departures as the sum of those inter-arrival times. So usually you imagine that you have a queuing system like this. Arrivals, something happens, something happens, something happens, and they leave. And you can have, you can have multiple stations and all sorts of things. But typically right now we're just talking about this part, the arrivals. Okay, a simpler way to find probabilities is again to look in the table. So if you go back to, I forgot, page 950, something like that, in your book, you will find that you can look up the arrival rate of 3, 4 arrivals in the next half hour, give you a probability of 0.1680, so the probability of 4 or fewer arrivals is just a question of adding together those numbers. Questions on how to read the table? Okay. I'm not going to provide you with a table. You're welcome to use them, but they're usually I end up making questions where you can't use the tables. Yes.
I was just a little bit unclear. That is using the arrival rate of 3. What's the probability of 4? Is that
Of 4 people
arriving in the next hour?
half hour.
Okay?
When the average rate of arrivals is 3 per half hour. So as you might expect, the bulk of the probability is less than 3, right? Or 3 or less. Otherwise, you're not going to get an arrival rate of 3. And the smaller the arrival rate, the more the probability you get concentrated up here. Right? Okay. The last probability distribution we're going to look at today is the hypergeometric. You've actually seen something that was hypergeometrically distributed when we looked at poker, but we wait with it until now because it's so closely related to the binomial distribution. With the binomial distribution, we take independent trials that are identical, so they have the exact same probability of success each time. Now, it's very nice to be teaching statistics during polling season and primaries and whatnot. If you have exit polls, or if you're polling people at random, most of the time when you calculate probabilities, you treat this as binomial. But if you pick out someone and ask them who they voted for, are you going to pick that person again as your next observation? No. So, strictly speaking, is the probability that you're going to pick someone who votes for that same person going to be the same before and after you ask that individual?
You're limiting your potential samples by, you're reducing your potential sample by 1.
Exactly, and therefore the probability that you find someone who answers that candidate is going to change a little bit in which direction? If you've already picked out somebody who said they voted for a certain person,
You're going to reduce.
you're removing someone who votes for him from the poll. Right, exactly. But it's such a small amount in a country the size of the U.S. that nobody cares. Everybody just uses the binomial. But if you're looking at something like, a critical thing like the number of socks in a drawer, or, other applications, then the probability can change drastically. And the hypergeometric is used so that you take a sock and you simply recalculate the probability of picking out another sock of the same color. The formula for this is actually, again, something you've seen, and just keep this in mind. What we do is we have a total number of socks in the drawer. There are red socks, n minus r black socks. We want the probability of picking out x red socks, and therefore n minus x, little n minus x black socks, because little n is the number of socks we actually pull out. And therefore, big N choose little n. Different ways we can pull out little n socks from a drawer of big N socks. We'll look at an example. Let's assume that the infamously named Bob Neveready has 2 dead batteries and 2 good batteries, and of course he's confused as to which one is which. So he's going to randomly select 2 at a time. Well, actually he's going to randomly select 2. Let's first think about this from first principles. Bob picks out a battery. What's the probability it's a good battery?
1.5.
Okay. Now, how many batteries are left? What's the probability he picks out the good battery?
33%.
1 in 3, right? So, because the trials are independent, what is the probability that he's going to pick out the good battery the first time and the second time? Multiplication. 1/2 times 1/3, which is 1/6. Now, let's apply this to a hypergeometric. In this case, big N is what?
Number of.
I think we've all grasped the gravity of Bob's situation. Big N is the number of
Batteries.
So there are 4 batteries, right? How many batteries is Bob going to pick out? 2. How many of the batteries are good?
2.
2. And how many of the batteries, we want the probability that how many batteries are good?
2.
2. So the probability calculated using the hypergeometric is R2, choose x, which is 2, times big N minus r, so that's 4 minus 2, choose little n minus x. Well, little n is 2, x is 2, so choose 0. Divided by big N is 4, choose 2. The number of ways we can pick 2 batteries out of 4. Well, 2 choose 2 is 1, although I suppose I can. And 2 choose 0 is also 1. And so the only thing really we're left with is 4 choose 2. Well, I should have rewrite that. So these 2 first cancel out, 0 factorial is 1, and these 2 cancel out. So we end up with 1 divided by, now the 2 and the 4 cancel out, so we have 6. And I know that's not a derivation, but it just shows at least the formula is consistent with this one example. And in fact, of course, it does work out. Questions on the application of the hypergeometric? We'll do problems with each of these. Okay. And that is chapter 5. Does everyone remember what makes a random variable? Or perhaps I should rephrase. Does anyone remember what makes a random variable? something about the outcomes. Numeric, thank you. If you have only numeric outcomes and you can assign each outcome a probability, then you have a random variable. If you list all the outcomes and the probabilities, you have a probability table. If you at least have a rule to come up with all the outcomes and the probabilities, then you have probability distribution. And we looked at 3 different types. The hypergeometric we just talked about. Linked to the hypergeometric was the binomial. What's the difference between the hypergeometric and the binomial? What's that?
The last one is not independent.
They're both independent trials. Something else?
Probability is different.
On the hypergeometric, you don't replace after.
Exactly, excellent. So with the hypergeometric, we have no replacement, whereas in the binomial, remember, we have identical trials. Right, so it's the same probability of success each time, which with the hypergeometric, you have a changing of probabilities. And then finally, the constant you use when you're interested in the number of something that happens within an interval of time. Okay? The most difficult thing usually when we cover distributions is to remember when to use what. Shoehorning or fitting a situation to be applicable to a given structure. And like I said, the first time I had this type of problem and it counted, or it was, well, it counted for me anyway, I forgot. So it's very easy to, it really is very easy to forget when you can use such a tool. Okay, I usually don't sort of make a big deal about reading ahead, but continuous distributions are truly kind of painful, so it would be beneficial if you at least skimmed ahead and got familiar, a little bit familiar with the definitions and a few of the concepts. So we're going to do a few probabilities, and then we've got a request for some more, so I'm going to get started. Okay, probably room for this. How about that? We have a budgeting process. Where we have the following possible expenditures, 9, 10, 11, 12, and $13 million, and the following probabilities, 0.3, 0.2, 0.25, 0.05, and 0.2. So this is actually the answer to A. When you just asked show the probability distribution, you can either do that or you can come up with a bar graph or a histogram, but I actually prefer that. What is the expected value of the expense forecast for the coming year? Well, you multiply across. So 2.7 to 2.75, 0.6, 2.6, and that adds up to, let's see, 10.65. So that's the mean. We're also asked to find the variance of the forecast, and of course, what have I done now? I did not print this out. take each outcome, subtract the mean, square, and weight, add up all that, we get the variance of 2.1275. Now, what are the units here?
Millions of dollars.
Say again?
Millions of dollars.
Millions square, dollar square.
Okay, close. Remember, the units here are millions of dollars. So if you square millions of dollars, you get,
Million square.
well, right,
Dollars
it's million
squared.
squared if you put the parentheses ahead of the million and after the square, right?
Right.
So it's, or it's a million squared, dollar squared, otherwise. It's a very large number, regardless. And in order to get it back down to millions of dollars, you would take the square root of that. The last question we have is, if the income projections for the year is tell us we're going to get $12 million, comment on the financial position of the college. And there are two ways you can do that. At least two ways. So you're going to get revenue of $12 million. What could we compare that to?
Expenses.
Yes, expenses, good. Any particular numbers leap to mind? Okay, so 13 million, and what does that tell you? Okay, so we're gonna have a deficit. What's the probability of that happening? Okay, so one way of commenting is to say, well, there's a 20% probability that we're gonna have a deficit, right? That tells you one thing. And there's one other thing you can point out. No? Excellent, that's very good. But you could also comment on this. The expected expense is 10.65, so the expected net profit, so to speak, is positive. Yes? And in fact, that's one thing we could just compare to. There's an expected gain of $1.35 million. I actually think, since it's probably a non-profit institution, yeah, the 20% would lead you to at least line up a source of credit, if nothing else. Okay, so that's a probability distribution that's just discrete. Yeah.
I know this is stepping back at least a couple of weeks into definitions, but what is variance telling us?
It's a measure of the spread. It's actually not stepping back a couple of weeks because we were still doing descriptive statistics then. Remember, now we're dealing with just a mathematical entity, a probability distribution. But it is, again, a measure of the spread of the probability mass around a mean, around the middle. It doesn't have a sensible unit, which is why we take the square root. We still have, and then we have another measure that's directly, related, so monotonically related to the variance. But it also measures how spread out your probability is.
Okay.
Okay. Okay, let's look at problem 59. The unemployment rate is 4.1%. So we have a 4.1% unemployment rate. We are going to assume that 100 employable people are selected randomly. And we're going to be asked, first of all, we're asked, what is the expected number of people who are unemployed? How might we answer that? is
4.1
4.1, and how'd you get that?
out of 100. I mean,
Okay, so out of 100,
I mean, 4.1% is the unemployment rate, and you
Okay.
have 100
yes,
employable people.
so,
You're selecting 4.1%.
right, so strictly speaking, the actual mathematical operation you're doing is
4.41 divided by
1,000?
yeah.
I know it sounds painful, but I really want you to nail down what you're doing.
It's 4.1%. So
Okay, so this is another way of writing 4.1%.
right.
Now what?
Okay, and then which is nothing but multiplication of 100 and
Very good. So this we're going to call n, this we're going to call p. And what kind of distribution do you think we're working with? Based on that? Remember?
I think first one binomial.
The binomial, yes, this is a binomial problem. Now, it's only approximately binomial because clearly, if you pick out somebody, this is again the polling question, you pick out somebody and you ask them, are you unemployed? And they say yes. Is the probability that the next person you interview unemployed, is that the same? It's
Not
slightly smaller,
precisely.
right? So strictly speaking, this is hypergeometric. But because your sample size is so immense, we're treating it as if it's binomial.
Can you go into more detail on how we know this is binomial?
Right. Well, okay, the requirements for a binomial experiment are you have a fixed number of trials, right? 100.
100.
And you're picking out at random. These are independent. The probability of success is the same every time. In this case, success is,
Finding an unemployed person.
right, finding an unemployed person. And the key point, of course, is that the probability of success doesn't change from time to time. That's where we differ a little bit, right? Because in reality, it does change just slightly. Nobody's going to interview the same person several times. But it's close enough, and nobody worries about it. So 100 identical independent trials.
Thank you.
Oh, there's one other thing. You're interested in the number of successes. That's also kind of important. So we can also calculate the variance and standard deviation. And again, I don't expect this to be intuitive. The variance is NP and minus P. So that then is 4.1 times 1 minus 0.041. Or 4.1 times 0.959, which is a little less than 3 point something. 3.9319. Which gives us a standard deviation of the square root of that, which is roughly 1.99829. Because, a variance of 3.9 squared unemployed people doesn't help anyone. Okay, naturally, I would want to ask another question. I would ask you, what is the probability that you have exactly one unemployed person in your sample? How do we find that? Choose one, good. And what? don't use a standard deviation there.
The formula we used before?
No.
Okay, 1 of 1. 1, 2, 3.
So we're doing that. 100 choose 1.
Okay,
Then we have, okay, so this is the number of sample points where we have exactly one unemployed. Alright.
and
Is it times the probability?
Yep. So we can start with the probability of success to the power of the number of successes, right? How many successes?
1.
1. And then we multiply by 1 minus the probability of success to the power of the number of,
Failures.
exactly, or 99. Ring a bell? Okay, so that's 100 times this, that's again 4.1 times 0.959 to the power of 99, which somebody with a calculator is gonna have to do for me.
3.
How much? Messing in my head. I like that, that's kind of,
It's for that Hotel California reference.
only zero. So what is it really?
0.0158.
Really? Is that small? 0. What? Like that? Okay, great. So, of course, my next question would be, what is the probability?
That's without times and multiplying by 4.1.
Well, okay, so if you do that,
This is 0.0649.
there we go, okay. And if I asked you, what is the probability of more than one unemployed person? What would you do?
1 minus that.
Are you sure?
Was.
Well, that just means you're starting to read me. You're missing something. You missed it before today.
The total probability minus that,
Of what?
of people being unemployed.
Not quite.
Probability of no one.
Right. So hopefully by going over this a couple of times, it'll be memorable enough for the final. So that's 1 minus the probability that x is less than or equal to 1, which is 1 minus the probability that x is equal to 0 plus the probability that x is equal to 1. And, well, that's sort of the point, so we can stop there. Are there any questions on the binomial? Notice that you weren't told this was binomial, you were just described the situation, and then you applied the binomial. If you'd applied that for geometric, I would, that's not a bad thing, it's just, it's a really, really, really hard thing to do. I'm not sure your calculator or computers would really survive that exercise. Okay, so let's look at 61. And let me again read you the scenario that's going to tell you what to do with it. Cars arrive at a car wash randomly and independently. The probability of an arrival is the same for any 2 time arrivals of equal length. So that tells you we're dealing with what kind of problem? So, very good. The mean arrival rate is 15 cars per hour. What is the probability that 20 or more cars will arrive during any given hour of operation? So let's start with x being equal to 20 and find the probability of that. Well, if you remember the formula, it was, do I remember the formula? Mu to the power of x, so 15 to the power of 20, e to the power minus mu, x factorial. Right? And your computers can, and calculators for that matter, can do that. And this turns out to be some number that fortunately we already have. 0.00649. probability that x is greater than or equal to 20 is 0.049. If you were going to solve this problem, I would highly recommend using the table, because it's an easy job once you have the table. And I have broken it. Okay. That's a little too later, I think. Better. Okay, so up here, we have mu, and mu here is 15. And here we have x, we want the numbers from 20 and up, to find 0.0418 and so on. So just follow that down until you're hitting 0, you add up that column. Okay, any questions on reading the table? Okay, in that case, we will progress to the hypergeometric, which we're almost have for nostalgia purposes, because the problem has to do with poker. I am fond of poker, yeah, well, I'm fond of it statistically. It's not supposed to be a permanent marker. Okay. Somebody in the other class said that if you actually go over it with another marker, that'll remove the first one. Of course, with my luck, I'm probably going to end up with both of them stuck. All right. Fingers crossed. Okay. To be on the safe side. So we have a deck of 52 cards, 4 of which are aces. What is the probability that the deal of a 5-card hand provides a pair of aces, exactly 1 ace, no aces, at least 1 ace? So let's start with the obvious. We learned how to solve this problem from first principles last week. But if you just heard this problem, can you shoehorn it into a hypergeometric distribution? What do you need for a hypergeometric distribution?
No replacement.
No replacement, right? Do we have, and we don't have that here. Do we have? Okay, and independent hands being, or cards being dealt, yeah. We need one more sort of key thing. We need there to be how many classes of things?
Oh, outcomes you mean?
Yes,
2.
2. Only 2 types of outcomes. What are the 2 types of outcomes here?
Pair of aces are only one ace.
What's that?
Pair of aces are only one ace.
No. The 2 outcomes, okay, each trial is getting 1 card, right? And each card can be either what or what?
Success or failure.
Success or failure, this time called
Ace.
an ace or not an ace. Yes? Everybody happy with that? So again, you see we're shoehorning the situation so that it fits. We want the probability for a pair of aces. If we simply force the hypergeometric, we have big N, which is what? Total number of,
Outcomes.
which is
52.
52, good. we have little n, which is the number total.
One ace
Number
or
of
four
aces.
aces?
Little n is the number,
Aces?
you know, little r is the
That
number
we'll
of
pick.
aces.
Oh, success or failure, right?
Number that we'll pick?
Number that you pick, right? And if we're interested in 2, then, you know, that's x. So we get, just applying the formulas, we have 4 choose 2, times 52 choose, minus 4, that's the number of non-aces. Choose 5 minus 2, divided by 52 choose 5. And I think we spent plenty of time last week going through that type of thinking. So let's instead focus on what changes. When we find the probability of 1 ace, what changes in our formula? R is the number of aces in the deck.
X changes.
R becomes 3, and X
Well,
becomes
there's still 4 aces in the deck.
X changes the probability of getting 1 ace instead of being 2 aces.
That's what we're calculating, right? So x is now 1, and how does that change the formula? What changes here?
5 minus
5 minus 1 instead of
5 minus 1, that's true.
4 choosing.
4 choose 1, that's right, and that's it, right? These two numbers change. These 2 become 1, that's it. How about 0? It's the same thing.
Zero.
You just change this to 0, this to 0, and you're done. How about the probability of getting at least 1 ace? It's always a good idea to look at the last thing you solved, yes?
So it's either you could add the probabilities of x equals 1, probability of x equals 2, etc.
Right?
Or you could just subtract 1 minus the probability of x equals 0.
There you go. So this is at least the third, I think the fourth time we've seen this trick. Right? Calculate complements because it's easier to calculate what you're not interested in than what you are interested in. So if we apply this, we just get 1 minus 4 choose 0, 48 choose 5, over 52 choose 5. Questions on that? Okay, again, notice the real key here is just recognizing when you use the distributions. Okay, we're going to take a 5-minute break, and then we're going to go over homework problems that I missed from previous lessons.